let's ask a simpler question. Let's assume you have two infinite square wells. They have some states. And if it's infinite, the states terminate at 0 on the boundaries. Okay? So whatever you'll do, they will never tunnel from here to here. Okay. Now, let's change the question. We have now a finite barrier. Stills are deep in the well, but you have a finite barrier. So if you solve it, you'll see that you have here, it will go to 0, the wave function, because it's still and here it has some tails that dies out exponentially. Same here. Now, in perturbation theory, you can't just perturb from the point where it was infinite, because you have nothing there. You have to calculate the wave function for such a situation and see the overlap between the two wave function, and that's proportional to the tunneling. But something happened here. Your states here are not similar to the states here. You changed your Hilbert space. It's more pronounced if you put all of them on a finite. Because then, which you need for a lattice, right? You want it to go also to its neighbor in the left. Then these states are completely different than these states. Why? These are discrete, these are a continuum. So you change the nature of your wave functions in the perturbation. So it's not really a small perturbation. So people have worked hard on deriving some formalisms that can give you this estimation of the tunneling between. I have in my room here a book of about 300 pages which discusses how to do it. Mathematician will take that book and throw it completely out, because at the end of the day you have an overfilled an overfull Hilbert space here. You have more states than you should have in order to do this calculation, but empirically it works quite well. So in order not to get into all this discussion, what is really done is you have the spectrum and you play with beta and gamma in order to reproduce it.
Oh, but we'd still see the bands. How do we tell which is from which energy level? All we see are the energy bands, right?
No, but you see levels in the band. And you know the atomic levels, right? So you know the width.
So you know where it's meant to be, and then you see where they cross.
Indeed. Okay, so all this is not part of the course. It's an interesting question. You can understand why it's not getting into the course. Just a couple of administrative notifications. One of them, the replacement class that should have taken place on Tuesday is moved to Friday. So something to do with double booking of the room. So, when it was supposed to be 18. So the replacement class will take place on Friday between 10 and 1 in the same room. Okay, so this is cancelled. Time. Okay. And now regarding, I've started to get questions about the exam. So first of all, the exam, the regular exam taking place, I think, in the 19th of July, is an exam with open material. What do I mean open material? Whatever you want to write down or print down and bring with you, I don't care. You can bring Ashcroft, you can bring double copies of Ashcroft, you can download from the internet any material you want. The only limit is no electronic devices, for the simple reason that no one can monitor that you're not contacting someone else in order to get answers. So, studying for such an exam is somewhat different than a regular exam. First of all, people tend to think that if the material is open, there's no point in going over the material. That's completely wrong. It helps you to remember things, not to miss something that you missed, but there's no chance in the world that you will come to the exam and decide then first time to start to read your notes or Ashcroft. It doesn't work like that. You have 3 hours. You have to know the material. You can use it in order to refresh your memory, to check some points that you're not sure about. But even the simplest thing, knowing where the material is in your notes or your books, you don't want to waste time on that. Second, someone requested an example of an exam. So my problem with giving an example of an exam is the following. If I give you an example and do something different, so it's not fair, right? If I give you an exam and do something very similar, so I'm not checking what you have learned. So I never give an example of an exam. I would like to emphasize that it's much more beneficial to go over the lectures in Ashcroft and try to understand what's the reason behind the things that appear there than going and trying to solve any questions that you can find on the internet. It's useful to do some examples of questions which you have in Ashcroft and you have in all over the internet nowadays. You can download hundreds of exams from different institutions, but I don't think that just solving all of them in order to be lucky enough to run into such a question in the exam is useful. My questions tend to check more understandings than long mathematics or complicated calculations. So focus on understanding the material, not so much on solving an infinite number of questions in the material. Okay, questions about that?
Can you give us some, maybe pose some example questions that we could practice?
That's exactly what I
No,
referred to in the beginning.
I know what you said. It's not that. I said that maybe you can give us some examples of understanding questions so we can expect what will come.
I'm going back to the beginning. You're not in high school. You're not supposed to just digest some 40 types of question and spit it out in the exam. Your third year in your undergraduates, the point that you're supposed to really understand material, and when you're asked a question that you're not expected, think a bit and come up with the answer. Okay. So, semiconductors. As I said a few times in previous lectures, this is the most useful technologically things that you learn in this whole course. I hope to finish semiconductors and one of the most known use of semiconductors in electronics. Someone can guess what it is?
Transistor?
Diode, because a transistor is two diodes connected back to back. So we'll do the simpler device. And that's what I want to do in this week, and that will be till the end of the week. That's the materials that you'll have in the exam. Next week I'll do magnetics, magnetic phenomena in solid state physics. I'm dreading to say it, it's not in the exam, but it's nevertheless an important chapter in solid state physics, and you can't really convince yourselves that you know something about condensed matter without at least touching upon magnetic phenomena. So, as I said, I'm afraid that no one will come to the lecture, but nevertheless, the lecture will take place, and I think it's beneficial to learn that subject. Okay, so now we're moving to semiconductors. And as we discussed in the previous lecture, they are basically an insulator. So, the two interesting bands are the valence band and the conductance band. Of course, there can be also a whole series of other bands deep into. They're not interesting for at least room temperature properties, for the same reasons that when you're doing spectroscopy of atoms, core electrons or chemistry are seldom of any importance in the game. So the valence band is the top occupied band. The conduction is the top unoccupied, and since I said it's an insulator, I know that the Fermi energy is somewhere in between. Fermi energy, or mu, somewhere in between. And G is the size of the gap. And we'll start from the simplest semiconductors that we know, which is a pure semiconductor.
Excuse me, before you go on. In what conditions are is the conductance band unoccupied?
Zero temperature.
And so when you start adding temperature, it
And
does
that we'll spend the next half hour on estimating on the number
goes up.
of electrons that go up at a given temperature for a given gap. That would be statistical mechanics or Sommerfeld or exactly what we will consider here. Now, the second part of this lecture will be devoted to impurities. We'll see that a small number of impurities in this semiconductor will completely change the properties of the system. We'll try to understand why, and from a technological point of view, this is the basis of all the semiconductor industry that you have nowadays. It's a bit comical, but the first part of the semiconductor industry is very much devoted to create extremely clean semiconductors. Extremely clean in the meaning while in regular chemistry, a few parts per million of some impurity no one cares about. In semiconductors, you want to get much, much higher purity of the materials. So, at the beginning of the semiconductor industry, that was one of the main hurdles to use semiconductors in electronic industry was just to get pure enough semiconductors. So one is how to clean up all of the impurities. Second, when you create this lattice, you don't want defects in the lattice, meaning areas that are not exactly following the lattice vectors. There's a whole bunch of different phenomena that create defects in lattices. Actually, at the moment, human technology already for thousands of years put in a lot of effort in eliminating these types of defects. If you ever wondered why a blacksmith goes and hits with a hammer iron, part of the reason is to clean up the lattice from defects and create certain types of defects there that enhance the mechanical properties of the system. So human beings knew about that you can manipulate the lattice without understanding what is a lattice and why are they doing it. So if someone is interested, there's a whole chapter in Ashcroft that deals with it. We are not touching upon it in this course. So what we are touching here is assuming that we have a very clean lattice. By the way, this is chapter 28 in Ashcroft. No, it's not skipping because Ashcroft is not built in a sequential way. If you are wondering why we did all these jumps between chapters in Ashcroft, the reason is that usually, at least in a bunch of a few chapters in Ashcroft, you don't need any material from before or further on. Excuse me?
Weird way to write a textbook.
Well, because that's a philosophical point, but condensed matter is a different subject than quantum mechanics or electromagnetism or thermodynamics or statistical mechanics. Those are basic theories built one layer upon the other. It's very hard there to skip between subjects if you are not well prepared in the previous one. Condensed matter is a very different, it's more empirical driven. You have materials, you want to understand their properties. So someone is interested about the mechanical properties, someone is interested in the heat capacity, someone else is interested in electric conductance, someone else is interested in something else. They have touching points, but they could be treated, once you understand the concept of lattice, which is somehow the backbone of them all, you can go to each subject more or less as you please.
What is the difference between impurities and defects?
Okay, a very good question. Let's just draw a caricature of a lattice. Semiconductors are usually FCC or BCC, not simple cubic, but that's what I know to draw. Some example of defect. Suddenly a rod terminates and all the rods are squished by a bit. You have, if you would ever study metallurgy, the theory of metals, there's whole textbooks on all the different possible defects in lattice, how to avoid them, sometimes how to create them, because for some purposes they are actually useful. Okay, so that's a defect. What's an impurity? Let's assume that this is a semiconductor, so let's take the most ubiquitous semiconductor, silicon. Okay, I missed one on purpose. And here, instead of silicon, you have a different atom, which is the important thing. What is the basic property of silicon when we are considering its chemistry?
4 valence electron.
4 valence electron. So here comes something, and sorry that I don't remember, you can check anyone with connection to the internet. Something that has 3 or 5 valence electrons. Phosphate, for example. So what will happen here? It still will be arranged in the same lattice structure, but this guy will have 1 electron that it wants to get rid of, or 1 missing one, or 1 hole that it would like to fill. And that's an impurity. Someone that in principle doesn't change the lattice structure, but does something to the electronic properties. And we'll see that what it does is not so hard to understand, and that creates something that changes the structure of the bands, and it changes it even if the number of such impurities are 10 to the 10 lower than what is needed. Now, the second part of the semiconductor industry is basically using those impurities after we created a completely clean and perfect lattice. And basically this, until today, is part science but part black magic. People tried a lot of different ways. Some of them worked, and everyone is copying this. It's known as the cookbook. It came out from fire-chilled semiconductors in the Silicon Valley, and people who left it stole or not didn't steal. It's a whole issues that people sued and sued back and whatever these cookbooks. And the most important thing once you open such a factory for manufacturing is to have this cookbook, because nowadays to reproduce it will take you a long time, because a lot of things that are happening there are as I called it, black magic, just empirical test and see what works better, and that's something that's built on with years of experience. And now, after you have this pristine silicon, or it could be germanium, it could be gallium lattices, you go and push in impurities, and the important thing is to push them in specific places. That's an integrated circuit. So, okay, first, completely clean silicon or germanium or what have it, semiconductor, and we want to answer your question: how many electrons will move from here to here? So, in general, I'll call NC the density of electrons in the conductance band, and PV the density of holes, meaning missing electrons, in the valence band. And you get it just from statistical mechanics. So exactly what you expect. G is the density of states. This is probability. What is this exactly? Depends on your semiconductor. Go do tight binding. Go do nearly free epixons. Yeah.
What is epsilon seems?
Energy of the conductor.
Energy at the beginning of the conductance band. Actually, it was a right band. Now you can say, wait a minute, but you have bands higher, so why don't you write them down? It's exponentially expensive to move up. And in a usual semiconductor, within temperatures that the lattice doesn't melt, your probability of going to higher bands is 0. You don't have to worry about it. Okay. Why did I write holes? Same thing for holes. Density of state in the valence band. Why is it 1 minus? Because it's the density of holes. Holes is the absence of electrons. This is the probability of having an electron. 1 minus is the probability of having a hole.
The density of electrons in the conductance band is the density of holes in the valence band, because they all came from there.
That will be the next step. If I have no impurities, all electrons have to come from the valence band. If I have impurities, then let's say the impurities are with valence of 5 electrons, they could come from the impurities.
רגע, זה גם כן אבל בקונדקטנס ההורס, או שזה בוולנס?
Life from minus infinity, again, I don't care what happens there because the probabilities that I go below, have any probability of having a hole below the conductance, the valence band is 0. Okay, so I can do here simple manipulation and get just multiply this by this and okay. Since any insulator which has such a small gap in between the valence and the conduction band, that it's much lower than KDT for all practical considerations, is basically a conductor. So I'm considering the case that and therefore I can see. Under these conditions, leave this picture here. This is just a question of definition. I have to now define what is large N and what is large P. So, what did I actually gain from this exercise? In occupation of states in statistical mechanics, what is always the biggest problem? Calculation of mu. Right? Because mu is not Fermi energy, and we have to write down some constraint on the number of particles that will define mu. These two guys don't depend on mu. They depend only on the intrinsic properties of the band, no matter what is mu. And you see temperature, but nothing else. No dependence on mu. Now, if I take the definition of a typical density of states of a material, what did we learn in the previous lecture? What is the density of states close to the edge of the conductance band or close to the top part of the valence band? Yes, but what is the physical behavior there?
Like
Free particles. So I take just the density of states of free particles because I assume that I have a small number of electrons that move to the upper conductance band. I have just a small number of holes that are created because of that, and the free electron approximation of the dependence on energy on K remains correct.
Near the top of the valence band, free particles?
Yeah, we discussed it in the previous lecture on Tuesday.
But then when you're integrating PV, you can't say that because it's not at the top. You're just like
I am at the top because in the end of the day, if this is correct, this is the occupation, it falls off exponentially as I go up in energy. So the bulk of my electrons are close to the edges of the band, either the lower edge or the top edge. So I'm quoting here the results that we developed a few lectures ago about the density of states of free electrons. The only thing that I change is that the energy doesn't start at zero, but starts either at one edge or the other edge of the band. This is this thing. Behaves like square root of E, of course, because it's E is equal K squared, dE is K. So it's square root of E. And all the information about the band, as we discussed in the previous lecture, goes into the effective mass. Okay, so basically, principle, well, not in principle, this is an easy integral to perform because this is just an exponential. This is square root. Change variables, so square root will be the integration variable, and you're off to the races. You can do this integral. I'll just write down the result. Okay, that's nice, but if we want to know the occupation, we can't avoid determining mu. But here I can use the following observation. Let's look what happens if I multiply NC by PV. Okay, it would be NC PV. Okay. But I know another thing. Since the number of holes is equal to the number of electrons, I can choose one of them, call it Ni, the number of electrons that are not in the band, or the number of holes that are added to the valence band. And they should be equal, so it's Ni squared. I for intrinsic, that's the name. So the number of electrons or the number of holes in each band I can know without determining mu at all. Because of the fact that they're equal to each other. And basically they go down exponentially as a function of the gap. Larger the gap, the smaller is this is the number of electrons either in the conductance band or holes in the valence band. Okay, nevertheless, I would like to determine mu, the chemical potential. So let's write this down explicitly. What did I do? Only entered the explicit form of large N and large P here. And since I know that NC is equal PV, I know that just wrote it down explicitly. Took a line of both sides of the equation. Now I can see what we get for mu. Okay. For zero temperature, it's exactly in the middle, which makes sense. And we have a correction that goes like T when the temperature is higher. Okay? As long as the temperature is not high enough for our assumptions that we used for the development of this equation. Okay, so we know everything that we should know about a pure semiconductor. We know how many holes and how many electrons we have as function of temperature. Good. What happens if we don't have a pure sample, or for some other reason we were able to introduce electrons into the system? Very generally, and that's an important tidbit regarding your knowledge in semiconductors, what are the two ways in which you can get electrons into the system, or holes into the system?
Electric field or electrical field of some sort?
Exactly. Either you put in impurities, or you put in a strong electric field which moves mu above or below and introduce additional electrons or holes into. So that's a reason that actually you have two families of transistors. One which is impurity based, and one is field effect transistors. We'll see, to create a diode you have to somehow change the number of electrons and holes on both sides of the diode. Okay, but generally speaking, we can assume that somehow I have an imbalance in the number of holes and the number of electrons by introducing additional electrons or holes into the system. So basically what happens, NC minus PV is not equal 0. Or we can call the number of additional electrons is NC minus PV, delta N, or vice versa. If you have holes, it will be a negative numbers. Okay, but let's stop a minute and look back at the development that we did here. Until here, did we assume that the number of holes is equal to the number of electrons? No. So this result remains. So we can write down NC times PV is still equal to Ni, which is defined here. Excuse me?
Ni squared.
Ni squared, correct. So basically,
What did you wrote the
NC is put it in color code. Okay, NC is a plus and PV is a minus. Just manipulating what's written here. So, if we know delta N, we can know the number of electrons and the number of holes that appear here, even if we have an addition of electrons or hole. If it's an addition of electrons, this is minus, and you have more holes than electrons. Okay, you can go back to the equations that we have written here. And we get just by using these definitions,
NC is equal to 1 over PV?
MC is not equal 1 over PV.
But that's what you
No. You have here the exponential is 1 over, but this is the same. So it's not 1 is 1 over the other.
It's just a multiplication between the exponents and the n, right? That's what
Mhm.
you're saying. Okay.
All we did is use the definition here, nothing more. Okay, so impurities add electrons or reduce the number of electrons, but they do also an additional thing which is very important. And this is perhaps the centerpiece of why semiconductors are so important in technology. They create new states. And understanding it is actually quite simple. Okay. And I'll give you a physical intuition what happens here before going into the calculation. Okay, so what did I say? Okay, I'm doing my lattice, and for simplicity I'm assuming that I have here an impurity which has an additional electron. This guy has an additional electron. All other electrons, all other 4 electrons in its valence shell get covalent connections with all other atoms, and it behaves the usual way. Now, what does this electron see? Okay, if I'm looking on the nucleus of this atom, it sees de facto only a positive charge of +1 electron, right? Because to be neutral, it needs all 5 valence electrons around it, and it has only 4 that are in the game in the lattice creation. So, you would say, okay, I know to solve that problem. We did it in the second course of quantum mechanics. What's this problem called? Exactly, a hydrogen atom. We have an electron bound to a Coulomb potential of plus an electron charge, and that's a hydrogen atom. Nevertheless, 2 corrections occur here. One, this is not a simple vacuum. The whole mess of electrons and protons and heaven knows what. How do I put in a simple way that fact?
different potential.
Yes, but how do I write the different potential? In the simplest classical way.
Harmonic potential?
No. The potential is still a Coulomb potential.
And different mass.
That's the second thing. A different charge, or in more simple and a term concept that you already know. It's the same charge but a different dielectric constant. The electric constant takes into account the electrostatic response of the whole environment. Therefore, in vacuum something, in any material, open a table and find what it is. Same thing here. We have here a dielectric constant which is different than the dielectric constant of the vacuum. And second, what you said, the mass of the electron is not the mass of a free electron. It's the mass of whatever lives.
Effective.
It's the effective mass of an electron living on some kind of lattice. These two simple modifications change completely the behavior of this hydrogen atom. Why? Let's remind ourselves, the radius, the Bohr radius of a hydrogen atom. Okay, we have here the two problematic quantities that we discussed. The electron charge, which now should be replaced by E square over the dielectric potential. And we have the mass. It should be replaced by the effective mass. So, the radius of this electron orbiting the impurity nucleus becomes E times and for typical impurities or in silicon or germanium, the mass is smaller, E is larger, and we get a factor of 100 in the radius compared to the Bohr radius.
But this isn't from an impurity, this is just generally in a lattice. Where does the impurity come in here? Just anywhere
It gives you the addition, it gives you two things. What are the two things?
We said the dielectric constant.
No, the mere fact that you put in an impurity in the lattice, what does it do?
I know, create asymmetry.
No, even simpler. It adds you an electron. Without that, you wouldn't have this electron. And adds you a center of positive charge. If it would have...
Oh, it's a different kind of atom than the others, isn't it?
Right. If it would have been the same, you would have nothing. The lattice structure and the covalent bonds take care of everything.
And you end up with the same effective ball radius?
No, you don't have. It's
We
not.
just don't care.
You don't care. Then you go to the usual situation of treating it by tight binding or by nearly free electrons. Calculate, you get free electrons. This guy can't be free because let's keep the picture of one impurity in the whole lattice. It can't venture too far from this positive center because otherwise creates a huge energy in potential electric energy. Right? And that's...
So there's more protons in the nucleus.
Hmm?
There's also going more protons in the nucleus.
That's exactly why you have a plus there. So instead of orbiting like in a regular hydrogen atom very close, of order of half an angstrom, this guy orbits very far. But still you have here a positive and here you have a negative charge. Okay, the fact that it orbits very far, what does it do to the energy states?
They leave the first Brillouin zone.
Excuse me?
They leave the first Brillouin zone.
No. Simpler. Keep it simple. Yes, please? It actually squishes the scale of energy. For an hydrogen atom, you need 13.6 electron volts to ionize it. Here, because the radius is so far, the energy will be much smaller. If we write it down explicitly,
I thought the energy levels were just dependent on the. Wait. Oh. Oh right, yeah. Okay.
I'll write explicitly E for ionizing. But here, M becomes M star, the effective, and E squared becomes E squared over epsilon, the electric constant, and you would end up one-thousandth of the energy. So instead of 13 electron volts, around 0.01 electron volt. So let's consider what does it do to now an impurity that contributes an electron is called a donor. What does it tell you? Basically, that it has, if I have an electron that is connected to this impurity, with a small change of energy, I can make it a free electron. Instead of something that was of order, if you remember, 1 or 2 electron volts, 0.01 electron volt of energy is enough to move it to the conduction band. So effectively, I have here an energies connected to the donors that are on the verge of being in the conductance band. Small change in temperature, and they'll start moving up. Same picture for a donor, for an acceptor. So these are donors. A small addition of energy, so a hole from the valence band will move, an electron from the valence band will move into the hole that this revalence electron has, and you'll have a hole in the valence band. So adding donor impurities creates de facto electrons in the conduction band. Adding acceptor impurities creates holes in the valence band for any reasonable temperature, and reasonable is room temperature is definitely reasonable. So let's consider the simplest technological application of doping by impurities. Okay, you know, diodes, transistors, and so on and so forth. What is the simplest ingredient of a circuit, of an electrical circuit?
Source of
simplest.
Cables? A wire?
Exactly.
cables.
You are sitting in high school and you're building your first electric circuit. You need wires to connect the thing. Now, silicon, germanium, whatever semiconductor in the pure state doesn't conduct current, just for the simple reasons that it has no free electrons. Take a wafer of silicon, and nowadays they are building wafers that are as large as a meter or something like that. Pure silicon. Think about how exact the technology has to be to do it. And if you, I don't recommend, don't hold me responsible to any damage you do, but open any computer motherboard, you'll see black pieces where you have a lot of contacts attached to it. What do these contacts do? They put in voltage or current, and you want to connect one to the other. Of course, you have a lot of transistor diodes, capacitors, resistors, or whatever you want on this board. At the beginning, you actually went and soldered these pieces of metal to connect one to the other. Of course, the number of transistors that you can connect in such a way is tens. Anything more complicated than that, you'll have a whole zoo of wires connecting all kinds of transistors together, not a good system.
It's difficult enough writing it on a piece of paper.
Hmm?
It's difficult enough to write the logic gates on a piece of paper.
Right, and now you have to solder all of them together, and the next stage was actually they connected strips of metal on a plastic board that you still see in the motherboard that still has part of this technology in it. So it would be easier, you don't have to pull wires from here and here, you're just sticking them at effective point. But then they had the idea. Basically, you want to connect this guy to this guy, take the silicon and make it a conductor. How do you do it? Put in donors only in this region, and you'll have a wire connecting this guy to this guy. Of course, you'll put in transistor and diode and things to create a functioning, but basically, that's a procedure. Now, how do you do it? So the magic, and that's called an integrated circuit. How do you force impurities to go only here and not anywhere else? The system you actually put something that's called a mask on top of the silicon. You somehow clean up the mask at the areas that you want to be doped with impurities. So, and this is a complicated procedure of putting a, no, to put a mask is not complicated. Correct, but at least conceptually putting something everywhere, a mask, at least conceptually is not terribly hard. The point is that then you want to remove the mask at certain areas. So you have to do some kind of chemical change in the mask, which is done with light, that's lithography. Then use some chemicals that after this change eat out this part of the mask. Then you expose it to a gas of impurities. Then these impurities diffuse into the silicon, and then you have a feature. And at least for the last, well, up to a decade ago, well, it's still going on today, the whole game was, how do you put more and more delicate features on top of the mask so you can push into this system more and more connecting wires, more and more transistors, more and more diodes, and nowadays the scale of these features that they are able to put on is a few nanometers. And
Wavelength of the light.
exactly, and moving from a few hundreds of nanometers to a few nanometers was a heroic struggle. It's a whole complicated technology in optics, actually, to get these features in such detail. What happened lately? You can't move much below a few nanometers. angstrom is the ultimate scale, but you don't want tunneling between different features that will mess up the behavior of the circuit. So more or less in
Moore's law has come to an end.
at least in this sense, yes, you hit the bottom and you can't do, going much smaller won't help.
למה דווקא אינטל הצליחו להגיע, אמרו שהם מציעים טרנזיסטור של 2 ננומטר.
That's what I said. A few nanometers is,
שהציפייה שלהם זה לרדת לחצי ננומטר.
and that's quite complicated just because of tunneling and another problem that I don't want to get into, heat dissipation. Everything here creates heat and you don't want too high heat that will cause these impurities to diffuse into different locations in the silicon, but can argue if 1 nanometer, half a nanometer, but that's it. You can't move much lower than that. So what I would like to do in the next couple of lectures, see what is the influence of these impurities on the occupation of the conductance band and valence band. And second part is how a diode works. A diode is a device where parts of the device are, the impurities are donors and part of the device it's acceptors, and that creates a very interesting phenomena. Current goes in one way but doesn't go in the other way. Okay, so we'll continue tomorrow.